Welcome everyone to the edition 2021 of the International Day of Light celebrations at INL. We welcome you all, and before we start into the program, we will just wait a little bit until most of the registered users are joining us. And in a very short moment, I will share our presentation with you and introduce a little bit the agenda of today. I'm the host of this event, and I invited several researchers of INL at different career stages to join this event. And it will be very exciting to hear from all of them, from experienced postdocs to PhD students to master students, and also our facility manager of the Nanophotonics and Bioimaging facility is going to be part of this event, and she will actually show you some live real-time experiments today. So I think we have quite an exciting agenda. I will share my screen now with you and then guide you through the different points of today in celebration of the International Day of Light. So welcome everyone. We are celebrating the International Day of Light in form of an online webinar. This is the second edition that we are celebrating in this way, online, due to obvious reasons, still due to the Corona pandemic. But of course, this has always not always been like this. Some of you met us already in person at INL at various International Day of Light celebrations during the years. So welcome everyone online. Even though we cannot see your faces, we see you are there. There are right now about 30 participants who will keep you updated, and we are happy of each and one that is joining us for this exciting event. So after these welcome words, so I will just introduce myself. I'm the host of today's events. I'm Joana. I'm a research group leader at INL of the ultra-fast bio and nanophotonics group, and also I'm the head of the Nanophotonics and Bioimaging Facility, as well as a cluster coordinator, and you will learn a little bit what are these clusters that we speak about at INL. I will give a short introduction into what it is about, why do we celebrate the International Day of Light, and then provide you some overview about our organization, an intergovernmental research organization focused on nanotechnology, the only worldwide international organization in this field of nanotechnology. And then I have the honor to have my colleagues providing inspirational talks about 4 different topics, and is performing a live experiment on a very new equipment that we have in our facility. So some of us, internal also and external visitors, it will be the first time also for our INL colleagues, the first time to see this equipment live. Only very few people have been seeing this 3D cell explorer from NanoLive that we just installed about 10 days ago in our facilities for the first time. We will talk about how to join us at INL, either as an employee or also as a visiting student. So we will inform you about the different type of fellowship and internship programs, and then of course how to use the facilities and also to use potentially yourself these facilities either on hand or requesting a service. And then last but not least, we will have some roundtable discussions. I will invite my colleagues to speak a bit about these different topics, the motivations to work in light sciences, and we hope, of course, for your inspiration and questions as well, that you can post throughout the event in the chat or in the Q&A button. So you see on your screen the possibility to also ask questions, and I will be able to bring these questions to the individual speakers. And last but not least, this event will be accompanied by a quiz. So all the speakers were asked to So yeah, to post some questions, and you will be able to show how much you were learning, or just have some fun questions in between. And so yeah, thanks for joining us. I see we are already 40 participants now, and it's, yeah, again, welcome to everyone that is joining. We are happy to celebrate with you. For those that would like to participate in the quiz, you have the possibility to either just follow the link that will be posted in the chat area, or you download this app on your phone, or simply use the QR code, scan this, and you will be falling directly onto the Day of Light quiz that we prepared. Why do we celebrate the International Day of Light on this, normally on the day, the 16th of May? The 16th of May, 1960 was actually the day that a laser has been successfully operated for the very first time. But as you know from last year's celebrations or from other advertisements, yeah, a laser is a very important tool that is bringing lots of innovation to us. You have a small laser diode in your CD drive, if you still have one. You have lasers for microfabrication. You have high power lasers to be involved in cutting metal pieces, in being used for bioimaging, which is something we are going to see today. And potentially, you know that light technologies are used to address the various societal challenges that we are facing today, and that are put into the Sustainable Development Goals by the United Nations. And so, as we are all aware, right, we have different aims that we try to tackle by different political decisions, but also to perform research and innovations to find solutions to the benefit of society, to the benefit to reducing poverty, hunger, to increase the well-being of the citizens, to provide high quality education, and so on and so on. And you will see that, of course, I mean, this is, I don't want to skip the other topics. Each and all of them are highly important to us. And you will see that some of these areas can benefit from photonic technology. So of course, as we are a research organization and interested and expert in research, we try to share with you what we can contribute with our light technologies in some of these areas. You will hear about light technologies for energy, for developing renewable energy solutions that, of course, are connected to climate neutral society, and also for health applications, biosensing, but also information communication technologies. So you will see that it's not by mistake that the logo of the International Day of Light has this very colorful shape. So you can see the Sustainable Development Goals are represented by these different colors, and the Day of Light logo is quite similar, because light technologies may have an impact in most of them. We have been celebrating already directly on the original day, the 16th of May, the International Day of Light, by providing a video to you. You can check this on the INL YouTube channel. This video allows a peek into our laboratories, and you will see members of our research group performing experiments in the lab and several interviews. It is around the Nanophotonics research groups at INL, led by Martin Lopez Garcia and myself. And so please watch this if you want to also get this inside lab perspective. We are, of course, not the only ones that are celebrating this International Day of Light, but there are worldwide events happening, especially during this week. So the week before and after the 16th of May. And you can see here the always updated event map of events happening all across the world. And in Portugal, you have several ones occurring now at the same time or slightly delayed or before, like photo competitions and other ones. And of course, you can see here our INL International Day of Light celebrations in Braga, hosted in Braga. As I mentioned before, this event has not always been a webinar. We started with inviting a few student groups to INL. The first Day of Light event in person was in 2016. And then we started to grow on site in 2018-19. We usually had topics of different research groups presenting how they use light in their research, if it is light for energy, light for sustainable environments, light for health applications or material processing. And some of our researchers actually successfully participated in some of the International of Light photo competitions. Here, a picture with the photo credit from Jean Martins, one of our PhD students in the group, who submitted a contribution of an image still recorded at the Champalimaud Foundation in Portugal and Lisbon. And so he was one of the winner of this contest. So you can find his images on all these photo galleries, also disseminated via the Day of Light org. Then last year, as I mentioned earlier, was the first event that we were holding in an online format as a webinar. We had a similar format with inspirational talks, this time from 4 different research groups. You can rewatch it under this YouTube link. Simply go to the INL YouTube channel and you will find this video. And also Mariana was presenting the Open Access Facility programs last year. Before going into the event, I wanted to give you a short overview about our organization. So we are based in Braga, in Portugal, but we are an intergovernmental research organization that was founded by the 2 member states, Portugal and Spain. So we have our official language at INL in English, and we are of international nature. So maybe it's an interesting detail that we are diplomats as a researcher at INL. So when you enter the INL grounds, you are basically stepping with your foot outside of Portugal and stepping on international grounds. Why did these governments decided to do this together? Because they had this vision that nanotechnology is also providing solutions for the benefit of society that may have an impact in both of these countries, solutions to tackle health, food, environment, energy, and then information communication technologies or future emerging technologies opportunities. And this did not change. So we see that nanotechnology and nanophotonics can have an impact in all these areas, and we are trying to explore the interfaces between disciplines, explore the interfaces between cultures, explore the interfaces between materials, and so on. That's our mission. And the vision is to be a recognized leading global nanotechnology innovation hub. So this articulates that we are developing solutions that are mission-driven, that aim to help the society in overcoming some of these global challenges and providing solutions that can enhance the quality of life. In the last year, and that is maybe for those that were participating last year and have already seen maybe this part of the INL historic description, they may not have seen, or they for sure have not seen, this new slide. By the way, now we are about 50 participants, so thank you for joining, everyone. It's really exciting to see you all here. So we have been developing something completely new at INL. We are 25 research groups But now a new scheme is to bring these research groups that have a focus and an expertise in a specific area together to explore interfaces by bringing them into discussion groups and in bringing them together in developing new missions that we can solve together by these interdisciplinary teams. So we have dedicated clusters where we discuss and develop solutions in the area of food, health, clean energy, sustainable environment, smart digital nanosystems, and advanced materials and computing. Based on the discussions that we were holding over the year, we developed different research programs into which we are focusing our efforts to develop new solutions that are deploying nanotechnology. And you can see here the vast map. Many of those are actually using photonics or photonics solutions, either intermediately or at the core. And with this, I will like to invite you to the inspirational talks that are discussing these some of the solutions that are pointing into these different areas. If they come from energy, information communication areas, neuromorphic computing, which is a new paradigm in computing, more related to the idea of the advanced materials computation clusters, and then again, areas where you can use photonics more in the areas of health, providing biosensing solutions for precision health tech applications. And then our new tool, which we hope to deploy, of course, for meaningful projects, either our own projects at INL, potentially related to health technologies, as this technique will be able to follow nanomaterial interacting with live cells in real time. But also it will be open, as you will see, for external projects to be used. So if you use these in our open access facility, you can also potentially deploy it for your own research in case you are from outside and you need this type of technologies. So with this, I would like to welcome Alessandro Cavalli. He is a Marie Curie Fellow at INL. So he came to INL with a prestigious individual fellowship grant. He did his PhD at the Technical University of Eindhoven, and then went to the US, actually to the state of Colorado, where in the town of Golden, he was working at the National Renewable Energy Laboratory, and now is at INL working in the group of Sascha Sadewasser, which is focused on nanostructured solutions for solar light harvesting, the laboratory of nanostructured solar cells. Alessandro, you're welcome, and the stage is yours. So feel free to start your presentation.
Yeah. Can you unshare? Yeah. So I hope you're seeing the presentation. Okay, so perfect. Yeah, thanks a lot for the kind introduction, Joana. So yeah, welcome to my talk. I'm Alessandro Cavalli. I'll give you a short introduction to myself and my work at INL. So first of all, I'd like to share my background, let's say. So I'm Italian, and after being born and raised in Cologne, not the German one, but the Italian one. It's a relatively small village, halfway between Milan and Verona, in Franciacorta, which is kind of the Italian equivalent of the Champagne region in France. So after I was born and raised there, and I started studying physics at the University of Milan Bicocca. And for my master's, I started focusing on solid-state physics, which allowed me to gaze into nanotechnology through my work on the thermoelectric properties of nanowires, for my master thesis at the Technical University of Munich in the framework of the Erasmus program. So that put me in contact with the nanowire community, which was my future for several years. And for my first step, I wanted to do a PhD in the deposition or the growth, how it's called in the community of the nanowires. So I contacted one of the leaders in the field, is Professor Erik Bakkers at the University of Technology in Eindhoven. And as I moved to the Netherlands for my PhD in applied physics, and there I entered the magical world of solar cells. And I was doing it all. I was preparing the substrate. I was growing the nanowires themselves and making solar cells out of them. And between some good results and some struggles with the dust culture and the life of a PhD, I was quite enjoying my time. But after I finished my PhD, it was time for a new adventure. So in 2017, I moved to the United States for a postdoc at the National Renewable Energy Laboratory, where I was working on both improving the performance of solar cells so that their efficiency is higher, and on making them cheaper at the same time. And after 2 years in the US, I successfully applied for a Marie Curie individual fellowship at INL, and with a project still on solar cells based on copper, indium, gallium selenide nanostructures. So now I'm here in Portugal, and since a year and a half, I've been working on developing materials in novel shapes and new architectures. So now that you know a bit my background, I'll explain what I'm actually working about. So I mentioned solar cells, and also Joana mentioned solar cells a few times, but for those that don't know, the important thing that I just want to mention for these 5 minutes is that the basic idea is that in photovoltaic devices, you have light coming from the sun, usually, that is converting into our device to generate electricity. And this is kind of, for me, a bit different approach or a different thing that you'll hear in other presentations today, in meaning that the light doesn't actually have an active role in photovoltaics or solar cells. It's kind of a passive element that is used to produce energy that can then be used for any purpose. But instead, what you're going to hear later is that the light is actually the active element, and you're trying to probe structures or make photonic computers. So it's like the light is the center, while here we are just using the light to do something, basically. So the best solar cells that have ever been made have an efficiency of 47.1%, and they are a very complicated structure with 47.1 efficiency, and they use 6 junctions. So it's 6 different materials, but actually to connect everything and have everything together working, you need more than 100 different material layers. So this is an exceptionally complicated structure that is bulky, it's thick, and it's difficult to use and deploy in uses such as vehicles and building integrated photovoltaics. So for this reason, we are investigating copper, indium, gallium selenide nanowires solar cells, which kind of look like a forest of columnar nanostructures that are a bit resembling trees, and they allow to save material and at the same time also increase the performance. So how do we do that? How do we make these nanowires? So at this moment, there are very few reports on this kind of nanostructures. So what we focused first is on demonstrating that we can actually grow this nanostructure or these nanowires. So, and the first step is to organize the growth. To do that, we organize a platform where our nanowires will grow. And we do that by defining islands of aluminum oxide on a silicon wafer using electron beam lithography in the clean room. And to do the growth then, we use molecular beam epitaxy. That is using very slow growth rates of about 1 nanometer per minute, allowing exceptional material quality and precise control of the growth. And here you can see a slightly sped up video of operating the machine, which is under ultra high vacuum, so it has to be handled with remote levers and mechanisms. So once the growth is done, we remove the samples through a load lock, and we characterize the samples through a series of measurements, mostly by scanning electron microscopy and other techniques like Raman spectroscopy and X-ray diffraction. So here I just show you the first demonstration of our site-controlled copper indium selenide nanostructures grown by MBE. And for the future, we are hoping to develop devices based on these structures. So with this, I have finished, and thank you very much for listening.
Thank you very much, Alessandro. There will be some time for questions, so if you have some questions now, please feel free to ask them. And you can post them via the chat. I haven't seen this video before. This was you, yeah, in the lab mounting, setting the setup into different detection modes. This was yourself, Alessandro?
Yeah, that was the operating the MBE. It was originally used for a flash talk at our INL seminar a few months ago, but there it was a full video, so I had also music, so it was a bit weirder. But I thought it was a nice example of showing how to...
Yeah, very good. Very nice.
How it works, and because the growth itself, it's difficult to show something. So everything is under high vacuum, so it's strange.
Very good. Yeah. So there's something in the question and answer session. Thibaut Courchou is asking, I'm not sure if I pronounced your name correctly, what is the range size of these fabricated structures? How small can it be? And is there a way of manufacturing it?
Yeah, thanks for the question. That's a good question. Actually, I didn't go too much into details. Basically, the structures are between 100 nanometers to microns in principle. We've seen some structures being above 1 or 2 microns, let's say in width. But in principle, in nanowires, it's quite common to also go lower and do like 10 nanometers of diameter, or even less. And for manufacturing, at the moment, we are using MBE because it's probably the best way to make it as precisely controlled as possible. But we've been also using magnetron sputtering for this, which is kind of well established as a tool for solar cells also. So I guess that would be the answer. Yeah.
There's one more question. Kanan MR is asking, what is the difference between 2D and 3D perovskite solar cells?
Well, perovskite solar cells are not exactly my specialty, but I guess that these nanowires I'm showing is more 3D because they're kind of isolated structures, while 2D usually they're just a thin film or a slab of material. So that by using 3D, we can kind of treat the nanowires as antennas so that we can save material by still having the same absorption and the same current, basically, so kind of the same performance, but using less material. So that's one of the...
Thank you very much. And one short follow-up question also again from Thibaut Courchou. Can they be polarized to make their movement controllable? And he thanks you for the answer already that you provided and says it was a really nice talk.
Okay, yeah, thanks. Well, for the polarization, in principle, actually polarization is a kind of an interesting topic for this kind of nanowire solar cells, and there's a lot of studies about what happens to different polarization of light when they encounter the nanowires. So that's kind of a big field in itself, because you can tailor different waveguide modes by tailoring, for instance, the diameter of the nanowires or the dimensions. So in principle, you can definitely polarize, and also you can use the nanowires to emit light, and then you're basically you're controlling the polarization with the same idea by changing the dimensions of the nanowires.
Thank you very much. Very interesting. So with this, thank you, and we introduce the next speaker, Ricardo Adão. He will speak about light modeling and, oops, I'm sorry, and engineering. Didn't want to move yet to the next slide, which didn't have much more information, but you should still see Ricardo when I introduce him. So about light modeling software, he will present some of the software that is custom developed, mainly by him, and that is an openly available software package that you can actually also use yourself. And he will show how this can be applied in different areas. One more connected to information communication technologies, mapping of LoRa signals, and another application in developing 3D waveguides for neuromorphic computation. Ricardo is a PhD student in the group. He is in his final stage of the PhD, so he has a lot of results to show, and he will dive deeply into how to model light interacting with nanostructures. And I have to warn you that there's this one or two little equations in there, but he will guide you through that and show what you can do when looking into these equations a bit more in detail and bringing them to life. So thank you, Ricardo, for starting your presentation.
Hello. Hi, everyone. Thank you very much for the introduction and for scaring my audience, which hopefully is not the case. So yeah, indeed, my name is Ricardo Adão, and I'm a PhD student. And today I'm happy to present my work on modeling light and engineering light-based information communication technologies in neuromorphic computation. So this particular piece of work that I would like to share today actually came up as a kind of a side project to my PhD, essentially because I needed to do some photonic simulations of some microstructures, but on the one hand side, I didn't have the right software. On the other hand, as coming from an engineer background, actually, I didn't dive enough into the Maxwell equation theory to really understand finite difference time domain. So I guess what I asked myself was, isn't there an easier way to do this? Like if I just want to do wave propagation, can I not simply model it as a mechanical wave, a little bit like a wave in a water pond? So it turns out that actually this question has been asked before, maybe 100 years before, into something that's very commonly known as the Lorentz oscillator model, where the oscillating motion of atom bond electrons is used to map the electric field in a material when excited by an external electric field, as you can see in this term here. What I did turned out to be a little bit similar in terms of the expression, but different in concept. So instead of using bound electrons, I defined these massless oscillators that are essentially electric field carriers. So you can kind of think of them as photon states. And then the interesting thing is I coupled these oscillators in a mesh so that I have like a map of these coupled oscillators. And they are coupled together. So each oscillator is coupled to its neighbors by a coupling strength defined by this gamma function here, which essentially determines the electric field rate. So the rate at which the electric field travels from one oscillator to the next, thereby just defining the speed of light. So with these two parameters, the coupling strength and the absorption coefficient, actually it was possible to model the wave propagation. So in order to turn these equations into a simulation algorithm, all I have to do was something called a leapfrog backward time differentiation, which is just about the simplest way you can do to discretize time into small time steps. And by working out these two constants here, to make it a physical model, I actually came up with this final solution. So not for everybody, but if some of you are actually not too happy to look at equations, you can trust me that this is probably the simplest finite different time domain method you'll ever look at, because usually they are so much more complicated. They have multiple field equations for different fields, different polarizations. Here is just one single field equation. There's no linear equation systems to solve. There's no matrix inversions to be done. It's just one simple field update equation that allows you to calculate the electric field over time. And if you're still not happy with this equation, I went ahead and made it a little bit easier by writing this little piece of software here, which I will demonstrate in a little bit of a tutorial on how to use it. So essentially, this is what it looks like. So we have a panel that allows setting the simulation parameters. So essentially the world size, the resolution, the wavelength, and some boundary conditions. So essentially you set what happens at the boundary of the simulation space, and then of course the design. So I have a pre-made design here. All I'll do is just comment this line, and I'll set preview. So this is our design just to test here in this session. This is called the photonic ring resonator. So essentially we're going to pump light on one of the arms and see what happens once the light travels inside the structure. And to have light inside, one thing we have to set is the light source, which is already predefined. You can do it all by interface. So you could, if you're a bit of a, let's say, advanced user, you can do it also by script. So I pre-filled all these items to have the light source there. You can choose its size, if it's a line or a point. You can modulate it either as a Gaussian or just a continuous wave. Of course, you set the wavelength, and then really all you have to do to run the simulation is press start. So by doing so, you can see here the light propagating. And with the video call and the screen sharing, this is actually quite slow. So this is usually maybe 3 to 4 times faster than right now. But I was foreseeing that this was going to happen. So what I did was actually, I calculated this for 2 wavelengths, and I put here the results. So usually this should take like maybe 30 seconds per simulation. What I did here was doing 2 wavelengths. And essentially because of the let's say the ratio of the ring size and the wavelength, depending on the phase between this upper waveguide and the ring, you'll have either destructive or constructive interference. And this is a very commonly used structure as to use in filters or photonic integrated circuits. It's really, really famous. So this is the example. You've seen all the process. Besides the ring resonator, we actually tried it on a lot more structures. So we tried the multimode interferometer, of course, the ring resonator here also in polychromatic light. So it's not limited to monochromatic light. We tried photonic crystals and sub-wavelength waveguides, and also Mach-Zehnder interferometers. You will learn a little bit more about this one in the next talk, so I'll not dwell on it. But essentially, we've tried it all, more or less. All the common building blocks of dielectric and semiconductor photonics, we can do it with this really simple model. And we found we can do even more. So because of its simplicity, we challenged ourselves and we tried, what if we use this method to simulate a signal propagating in a city? So we did that using a technology called LoRa, which is a wireless solution for long range and low power. And essentially we simulated the signal strength in a city using Google Maps data. You can see here the signal strength in dBm. And then experimentally, we also characterize the coverage area. And so by comparing the 2 of them, we have got actually pretty decent results. We've got 84% overlap in terms of area. And we also compared the edge of the 2 of the experimental and simulated coverage areas. And we actually got a root mean square error of only 24 meters, which if you compare it against other models that simply give you a range, which is essentially a circle. If we compare it against the best fitting circle, we get roughly twice a larger error. So it's really cool that we can use this not only for photonics, but also for any other applications in any other wavelength range, from UV to terahertz to radio frequency, any. Furthermore, we also, and this is a bit more related to my work, we're now using it also for 3D structures. Of course, in this case, it has to be only a set of 3D structures can be modeled with this 2D algorithm. But essentially, we're having a photonic artificial network where the network itself is planar, but we're using these 3D waveguides to interconnect the planar neurons using this kind of design. So essentially, they are supported ellipsoids. And we, in simple cases, we can use this also to simulate the light emitting from the light sources, how we can couple it into the structures, and also because of its simplicity of the method, how does it propagate throughout an entire waveguide, which is very difficult to do usually in finite difference time domain because of the sheer size and time it'll take for the simulation. So in summary, we've learned about this new technique called OFDTD, the oscillator finite difference time domain. And we've seen that it's actually, there's myriad applications you can use it to, from photonics to ICT to neuromorphic computing. And thank you very much. I'm here to answer any questions.
Thank you very much, Ricardo. So please post your questions in this Q&A area. So Ricardo is available to answer those. And yeah, it's quite exciting that this tool can be used for so many applications. The simulation plane is only in 2D, right? So, but how do you achieve, further on also using this model for 3D components?
Yeah, so for 3D, actually, what you're doing is still a 2D simulation. So if the 3D structures themselves can be simplified into a symmetry plane, then we just simulate a cut through the symmetry plane. But if, of course, if we had more complex structures, for example, with a modulation in X, Y, and Z, then we could not do it with this model. But the interesting thing here is the size of the waveguide, which typically it's not really simulatable with these kind of wave propagation algorithms because of the size of the memory that it will take, the CPU requirements, and the time it will take to run the simulation.
Okay.
And that
and
is only achievable.
Say one more word on what you need to have installed to be able to run the software.
Okay, so running the software, the only thing you need really is MATLAB. So there's no real installation. Usually, you can find this software online. Actually, it's there's a DOI for the software, and you can find it in Optics Express as well. So all you have to do is download the zip file and extract it into a directory. Tell MATLAB, you set it as your MATLAB path so that MATLAB knows that the software exists, and then you just call Wavebox on the command window, and that's it. Then you run it.
Okay, thank you very much. So we are curious to hear your feedback. If any one of you would like to use the software, I see there's one question that just came. How do you see your project or this software being applied maybe in biology or microscopy?
So a really fast answer, really quickly thinking about it. In biology, we can use it for biosensors. You'll see a talk about that right now, right next, when we're about photonic biosensors. So anything that's relying on refractive index contrast and waveguiding, you can do this really well with this kind of software. And we did it also with the Mach-Zehnder interferometer. For microscopy, I guess that's a little bit more in the realm of ray tracing, but you could in super resolution microscopy, actually, sometimes there's energy transfer processes that happen at a nanoscale, and I guess that could be addressed maybe with finite difference time domain approaches.
Fantastic. Yeah. Thank you very much. There's some more comments. Great talk, Ricardo, by Joyce Jakob. Are you planning to extend this software for 3D applications?
That's the million euro question. Actually, in the way that I've developed it, it's so simple that it actually, as I see it right now, it's not extendable to 3D, simply because this is using a mechanical oscillation, right? So that's okay to think about the water pond, but if you extrapolate to 3D, then you have a mechanical wave, like a little bit more like a sound wave, not like an electric field wave. So in electric field, you also always have the oscillation perpendicular to the propagation distance direction, and if you expand the OFDTD into 3D, this will not be the case. You'll probably have an oscillation that is parallel to the propagation direction. So it could be maybe for sound applications or vibrations, but not so much for electric field or electrodynamics.
Thank you very, very much for this great feedback and discussion. And thank you to everyone that was asking questions. And with this, indeed, the transition is perfect to introduce our next speaker, Joana Tatá. She is a master's student at INL, also in the Atofast Bio and Nanophotonics group. And as Ricardo said, there are ways to use photonic modeling for biosensing and using refractive index. And so you're going to learn about this in her talk on photonic integrated circuits for biosensing applications. And with that, I give the word to Joana, and please feel free to share your screen.
Thank you very much, Joana. So first, I would like to start by sharing a little bit of my academic background. So I am a Portuguese student. My master's is in micro and nanotechnologies, which is a master within the Department of Material Science of Nova School of Science and Technology. I was trained in microfabrication, nanofabrication, nanocharacterization, semiconductor science, nanomaterials, and I also engrossed in some extracurricular activities whose purpose was to disseminate the various fields and paths that a micro and nanotechnology engineer could take. So when it came time to choose my master thesis, I was already aware of what I could do. I was not sure of what I wanted to do. So I went back to some of the subjects that I liked the most. And I started to understand that all of them had light in common. So through friends, I learned that there existed a group entitled Ultrafast Bio and Nanophotonics group here at INL, whose purpose was to use light in nano applications. So right now I joined as a master student, and my focus of study is photonic integrated chips, which are inspired by integrated circuits, but instead of using electrical wires to perform electrical functions, we use optical waveguides to perform optical functions. And due to the nature, we can take these chips and apply them for biosensing. And the way that we do that is we utilize a phenomenon called evanescent field region, which occurs when we have light traveling through a waveguide by total internal reflection. So if we were to put an nanolight in this region, we will have a variation of refractive index of the cladding, and then the effective refractive index of the light traveling through the waveguide will vary, resulting in changes of some properties of the light in the output. For instance, the intensity of the light, the phase, the resonance momentum, or the polarization. Right now, in our focus is cubosomes. We are trying to measure these little lipid nanoparticles using this phenomenon. So, given this fact, we can create devices that can be label-free, which means that they will have a fast detection, at least compared with some other traditional methods. Given the fact that it will be a very direct way of sensing our analyte. We can also use this type of phenomenon to create point-of-care, low-cost, and user-friendly devices. But using a simple waveguide as a biosensor device is not recommended. This is because the output signal will be very dependent of the input light that we are giving the optical waveguide. And the variation of the signal will be very difficult to interpret. And so in my case of study, we are using Mach-Zehnder interferometers in order to get a response that we can easily interpret mathematically. So Mach-Zehnder interferometers are a type of photonic integrated devices. Ricardo has already introduced them to you. And they are the ones who are here in the middle. I was already a little bit familiar with them when I started to study a little bit my thesis proposal, but once I arrived to INL, I was given a short introductional course entitled Integrated Photonics Introduction Mini Course. This course was provided by Dr. Manuel Caim Garcia, Master of Science Ricardo Adão, and Bruno Romeira, for me to understand better how to manipulate and optimize these devices in order to get the responses that I wanted. I was also given more extendable knowledge in numerical in order to be able to simulate my devices properly, and was introduced to NASCA, which is a Python library focusing the design of photonic integrated structures. So that gave me autonomy to build my own chips. When it came to experimental procedures, I was already very familiarized with a clean room, since my background is microfabrication. And of course, it's a little bit different. When coming to INL, you will be facing a very big clean room with very procedures and very strict rules in order to ensure everyone's safety. But the trainings went very smoothly. And right now I am using two main machines, the manual spin coater and hot plates for various baking steps, and the electron beam lithography. The biggest learning curve for me was the optical characterization. I was not familiar at all with optical stages, coupling waveguides inside photonic chips. And so I had a lot to learn about that, but all the way through every every step of the way, I had my supervisors with me, and they ensured that in a matter of weeks, I was already very comfortable with handling everything. I was also introduced to MATLAB and MATLAB scripts in order to read and analyze my data. So my thesis proposal was done by Dr. Joana. She is the host of today's event and also the leader of the UPNP group. I contacted her through LinkedIn once I knew that I wanted to do my master thesis in her group. And very fastly, she had a thesis proposal for me. And so I contacted Professor Manuel Mendes, which is now my co-advisor in my faculty in School of Science and Technology. So I entered INL. And once I entered INL, I was introduced to Dr. Manuel Canho Garcia and Master of Science Fernando Gordo, which were my closest supervisors. And basically, they taught me everything that I know in my case of study now. So they taught me from the theory of the devices, from the microfabrication steps, and even from the characterization of the chips. So why come to INL? Obviously, when you come to INL, I think it's sure that you'll be working with top experts at their field, so you'll learn a lot. In science, people want you to learn a lot, so you'll have a lot of work to do, but it will be rewarding work. And also personally, I think that as master students are in a very raw phase of life. We don't even know what we really want professionally. And I think that by leaving the academic environment, you gain more confidence and more independence, and you are able to make your future choices better. At least that's my private insight. Thank you very much. I don't know if anyone has any questions.
Thank you very much, Joana, for your great presentation. If there are questions, please write them again in the Q&A area. I will then share the screen again. Joana, if you release yours, I can. There's some feedback. Nice presentation coming from participants in the chat window. Okay, so I think if there's no question, my question. Well, you said now you were introduced and you heard about our group. Did you hear about INL before? And if so, in which context do you remember this?
So since my academic background is micro and nanotechnologies, I was bound to hear about INL from the moment I started the degree. But yeah, every professor in every year will point some work that INL researchers will be doing. And we all know, all the students of my degree know that this is a top institution, and we always have the possibility of doing some master thesis here, even if not by contacting supervisors. It's already a possibility that we have. So yeah, I think I answered it, I'm not sure.
Okay, yes, sure. Thank you very much.
Thank you.
Okay, so then with that, we went through the different inspirational talks, and I will follow up with a very short info session before we actually look into our facility for a live experiment. So the two questions that I am going to answer to you, hopefully in a clear and not too long and boring fashion, is how to join INL and or how to access INL, and give a short overview of the open access facilities. How to join is very common, very normal procedure. So you basically have the possibility to look for open positions. On the INL website, you will see either our vacancies or be an associate panels. On open positions, I just took this screenshot today. So these are the currently open positions. They are all from the research domain, several research engineer and some research fellow positions, including one position as a junior research fellow position in our group, and in several other groups you will find opportunities as well. The application to the open positions always has to run via the job portal. Of course, you can contact the person that is offering the positions for further information, but the application is not via email, but always via the JobVite portal. And then there's the second approach to come to INL for an internship or as an associate on various levels of your career, from visiting master students that we just heard about from Joana, to visiting PhD candidates, like the example of Fernando Gordo, who is enrolled in a PhD program in Spain, but we have a collaborative project and he is visiting our group, or other groups would have a similar scheme. Or you are a more senior researcher and you would like to establish corporate agreement, and you could become a corporate associate and even a group leader at INL. So we have also several group leaders that are at the same time professors at the university, but as their strategic research agenda is fully aligned with the INL strategic plan, we have also some research group leaders that are officially associates of INL. Besides the career portal that I just mentioned that allows joining INL as a member of the personnel employed, where you could have different roles, either as staff researcher in a tenure track or non-tenure track type of position. You could find a research fellow, so postdoc positions, or junior fellow. Typically, after your master degree, you would enroll or apply to junior fellow positions. Research engineer positions that are typically also, there are also long-term positions as research engineers, as we have several engineer positions also in our clean room. And then, of course, some non-scientific jobs can be found if it's administration, legal, project management, site management, or communication. And then there's a different way to join, and that are the competitive fellowships. So this is, of course, no surprise that ESC grantees that come with an own fellowship, or they would like to apply with INL as the host institutions, are of course very welcome. So please contact us if you plan to submit an ESC grant and you think that nanotechnology is at the heart of your proposal, or you apply, as we heard today from Alessandro Cavalli, as an experienced postdoc that decided to apply to INL with his own fellowship via the Marie Curie program. So if you plan a similar application, ideally you contact the research group leader, find out if your research proposal is aligned with the strategy of the institution or the research group, and then you can get an endorsement for this application. The type of internships as an associate I just mentioned, so they are internships that may lead at your institution to a given academic degree. So for example, a master degree, so it would be a master research internship, or they do not lead to a degree, but your host organization is endorsing you to join INL for some time. That could be in frame of a traineeship, or you become project associates when you are a collaborative research project and you are performing some work of that research project at INL. And then the mentioned corporate associates, that is more for the established and senior researchers and academics. The open access facility programs are mainly covering our larger research facilities. The nanophotonics and bioimaging will be discussed a bit more in detail, then the clean room on the micro and nanofabrication, then advanced electron microscopy, and then we have some X-ray based technologies also available for you to apply. And I will just mention that all of these facilities are actually ISO certified. So this was celebrated some years back when we for the first time got the ISO 901 certification, as this is of course a level of trust, and it shows that we are also a trusted partner for academic and industry projects alike. Concerning the nanophotonics and bioimaging corporate labs, you will see that the type of technologies that we have can be deployed in various type of research areas. If you are coming from toxicology to drug delivery systems, nanomedicine, biophysics, developing your own microscopies or sensing technologies, we can help in either commercial solutions or our own R&D in-house custom developed microscopes. So on the right side, you will see the list, how it is presented on our INL webpage on the facilities, where you can find more information about all of these different technologies. Beside the commercial one, I think it's very important to highlight that the facility is also coupled to our R&D labs in photonics, where we are developing unique solutions such as combined AFM confocal microscopy, or confocal spinning disk microscopy, or multi-photon fluorescence lifetime imaging spectroscopy, or other techniques that are related to nonlinear microfabrication, where we can use a laser to build three-dimensional microstructures. We are part of the PPBI network, which was recently awarded to be a node in Eurobioimaging. So you can also contact us via PPBI. And with that, just following the webpage, you will find this button on Request Nanophotonics and Bioimaging Services. This will guide you into a platform where you can very shortly just write what type of sample you aim to study with which type of techniques. And if this is a clear information, and you will hear back from us in 5 days with your proposal, a quotation, what this would be costing you in case we are able to provide such service or access. And now it's time to present our facility manager, Mariana Carvalho. She is already in the facility, in the lab, in front of new equipment, and she will preparing, showing this, explaining a little bit the method, showing you the system running in real time live at the facility. So it's the time for live experiments using the 3D Cell Explorer from a company called NanoLive from Switzerland. The system was recently installed and tested, so we are all very excited, and I think also some members of NanoLive are watching us, and hopefully in case anything goes wrong are supporting us and helping to find a solution. But our experience is that the system is very robust, and so we decided to directly share our excitement with you watching. And just to mention that this system is funded by the project called Diamond for Brain. This is a project led by myself and in collaboration with 2 research institutes, the ICBS and the University of Aveiro Institute, and funded by La Caixa and the FCT. So thank you, Mariana, for your availability to show us this new equipment. And the stage is yours.
Thank you, Joana. So hello, everybody. So just to say a little bit more about our facilities. Just to remember that anyone doesn't have to be in Portugal, doesn't have to be in Europe. Anyone can apply to use our services. Just go to our website and send us a request. So today the idea is to show you this new nice microscope. I usually call new toys because for me they are big adult toys. So the NanoLive 3D Cell Explorer microscope is actually this little white box over here. It is not so big, and it is small, and it's very, very reliable. And in our case, we have an incubator as well. And right now I'm cultivating cells inside this microscope. I have a neuroblastoma cell line. So I will actually show you the system running. If it's a little bit too far away, maybe I can show you afterwards if you want to see more in details, a little video I've made earlier. But let's see how it goes, and hopefully it will, you know how experiments run. So sometimes they go easily, sometimes they they stop. But anyway, so let's start. So initially what I would do is that I would turn on LED light so I can focus and I can find my cell. I don't know if you can see here in the screen. I can see whatever I have over my sample. So I can share you the screen from the other side. Let's see if I can do that in an easy way so you can both see what I'm doing in the screen and also while I'm doing live. So let's see how it goes. So as you see, I can move around. I can choose like a place to do my image. Like the cells are being here for a while, so you see some kind of movement around. That's some cells floating and some other particles floating on the liquid. That's why you see this kind of wobbling. And once I'm satisfied with the area that I want to image, I can do a 3D single shot image for example. So what's going to happen is there is a small mirror over there that is going to rotate, and it's going to create we're going to illuminate the sample in different angles, and it's going to create a hologram. And from that, it's going to create a 3D image. So I'm just going to give it a name. So it's checking so you can see the small mirror rotating above the sample. So now it's measuring, it's acquiring, it's calculating. So I had the system already calibrated, so that's why this was a little bit faster. But now I have actually a 3D image from the cells that I was looking. So I can run through the different planes of the cells. I can see a 3D reconstruction. And actually what we see here is refractive index mapping. So for instance, if I can see each part of the cell has a different refractive index, so I can see the value and the gradient around. So different parts of the cell have different values. So one thing I can do is actually process the image to take the background, or actually get a better histogram to see more in detail. So let's apply. Okay. I can also create different color maps for different index of refractions. So let's choose something, for instance, this higher points over here. Let's see if it's gonna, yep. So I create some red over there. I can do some green over here. So I can move it around a little bit. Increase. So we can play around, create this false color maps, and have the 3D reconstruction over there. The nice thing is that also, since we have an incubator, and as I told you, I was cultivating the cells. Actually, those cells are over there for 3 days now. So I'm actually cultivating the cells inside of the microscope in this case. And we can do imaging over time. So like overnight, in 2 hours, 3 hours. I have a few examples for you. So I can show you now to share to my video clips. I'm gonna share you a little video we did for, in this case, is a 2-hour imaging for these neuronal cells. One image every 10 seconds. So you can see the cells moving, you can see them interacting. It might be a little bit slow. Usually internet connections do that. You can do this video also in color if you want. You can play, and everything you see over there is related to the difference of refractive index. So there is no staining whatsoever. So in this case, I'm not putting anything in my cells that would change her environment. The maximum would be something as the light that would have some interference, but it's so little light that goes inside that probably won't do anything. So we can study long-term cell relations and things like that. So if you have more questions, just let us know, and I'll be happy to help to answer those.
Thank you, Mariana. Excellent. I think everything was running perfectly. I believe the NanoLive experts that are watching are similarly excited about this as us. So yeah, I think it was a great idea to share this with you. Some of you might be future users of the system. So ask us any questions like what type of samples we can image, or how do you need to prepare your samples before being able to image them in the microscope. Maybe Mariana, do you want to give a few hints into how the samples should be prepared for you to be able to image?
Well, there are like, the applications can be different, but for example, the one restriction is that I have to have the access to the samples, and I have to have like a flat surface and a minimum volume of liquid, and the index of refraction of whatever liquid is around your cells should be as close as possible to the cells. So as the more transparent, the better. But you can actually you can measure in agarose, for example. We can render videos in color as well. But they always coded in depending on the refractive index. So the guy from
okay, and then Ricardo just posted on the chat also a question whether you can make a solid rendering of color, like representing a refractive index, in contrast to this transparent imaging mode.
Yes. So for example, in this case, if I can share my screen, Joana, over here. So if I can go back to the software. In this case, I'm creating opacity and transparency, so I can change the opacity and the edge softness as well. So they can be like the images can be a little bit like stronger, and you can actually also post-process the image using software like Fiji to create maximum projections and create videos. So there is a lot to be done. We are just scratching the surface with this new tool. So it's quite exciting to have a new toy and be able to learn a new technique. Okay.
Yeah, we're excited to use this, of course, for our project Diamond for Brain. We are going to study the interaction of nanodiamonds with these neuronal cells. And Adrian Baumann from NanoLive just wrote also to us, very nice acquisition, well done. So congrats, Mariana. And he would like to mention that they offer now also an automated integrated quantification tool within the software called Eve Analytics. So that's now also available. Yeah, so you can do this. Then there is one more question from Pedro Veloso. What's the time, the limit of resolution of this technique? Is it the same of traditional optical microscopes?
Well, hardly say, like we are always limited by the optical resolution. But in this case, since we're looking at holograms and phase and index of refraction differences, we can actually see smaller particles. I cannot say by heart the limit, the number. Maybe Adrian can help us with this because he might know it by heart. So to 400 in X and Y, 200 nanometers, and in Z, 400 nanometers. Thanks, Adrian. So, and that's really, really neat. But there are some, as I usually say that each technique is perfect for a different application. So depending on your application, you can have one technique or other working better for what you want to do. So every microscope is good, but it's good for a specific application.
Okay.
I hope it answers your question.
Yes, I think all the questions were answered. And if there are more questions, either contact Mariana or also the NanoLive team. And with this, we will transition to the very last part of the event, to our roundtable discussion. So I am inviting all the speakers of today together to join me on the panel discussion. And so just to reintroduce and just highlight it, that we have made the panel composition to reflect different career stages that would do researchers and facility managers at INL. So from experienced postdoc to PhD candidate, master candidate, and facility manager, myself also being able to report on, from more on the management level, from research group leader to facility manager and cluster coordinator. So we are looking forward to receiving a few questions from you before we start with the quiz. So we can maybe switch to the panel mode.
Stop sharing the screen, maybe.
Okay.
Yeah.
So if we are now in the panel mode, I would like to start with some question to maybe starting to ask Alessandro. So you presented today work that you have been doing related to energy, and materials seem to play a very important role. So I was actually curious to hear whether you see yourself more like as a photonics researcher or a material scientist, and if ever in your career maybe the reflection on that changed, or yeah, can you discuss this a little bit?
Well, I think I was always more on the material science side. I think it's mostly because with most of my career being in nanowires, I was more doing the growth and the deposition of the structures. I was always much more focused on developing the material, and then to actually doing devices and more advanced photonics. Actually, it's funny because during my PhD, I was basically, we had 2 PhDs working in the project, and I was doing basically developing the nanowires, and the other one was doing angle-dependent measurements and more photonics oriented measurements. But when I applied, I was kind of, let's say, offered both positions. So I basically chose, but I didn't really realize what I was choosing. So when I actually started, I was doing the growth, and he was doing all the photoluminescence and all the measurements. But it could have been the opposite. So, but I like doing the material science side more, I think.
It's very interesting. So can anyone else from the panel members also report on something that you maybe chose a direction in your career, and you were not really foreseeing in which direction it would lead you, and after some time you would see that you developed certain skills you were not expecting to develop by your career choice initially? Was this happening to you as well?
Well, not that my career has been very long, but I don't know what is the usual case in PhDs actually, but in mine at least, that was a little bit the case. So we had a project, right, and with a certain set of skills, and with nanofabrication of nano LEDs, and then suddenly, yeah, things unraveled a little bit differently. There came this simulation algorithm, there came near field interactions, there came all sorts of programming, instrumentation, and fun things that I actually didn't foresee. Now it's the time to actually cobble it together into a nice little thesis.
Okay, thank you. Joana, can you also comment on this? Like, were there like surprises about what you learned by making a choice to start working in nanophotonics? Did you learn something that you actually didn't expect to learn?
I mean, to be honest, everything was a surprise, because I was not even aware of this field. I know that I said that I know a lot of fields, even because of my extracurricular activities, but I don't know why we don't pay much attention to applications using light. That's a shame. We only talk about the very basics of optoelectronics and solar cells. So everything here was a big discovery for me. Photonic integrated chips, I think they have a really big future. And they can be applied to many different things. So yeah, I think I think that even though it were surprises after surprises and learning after learning, it's also a quick subject to pick on, because there's so much information out there. Even when you sent me the thesis proposal, I went searching, like in my thesis title, there is Mach-Zehnder. Now I was like searching what a Mach-Zehnder was and everything. And it's very easy to access now information. So I think you can counteract those surprises very well.
Yeah. Thank you for the feedback. Mariana, yeah, you certainly also can report on that. So facility management.
Oh, Joana froze.
That you have both in common, Joana and you, that Joana mentioned in her talk that she was engaged in an organization called NABU. NABU, right? And please correct me.
Nano.
So, okay, before I say it wrong, just say a word. What is nano? And then I will transition to Mariana, and she has been involved in something very similar in the past.
Yeah, sure. So Nova School of Science and Technology has many different nucleus, and some of them are academic nucleus, which means that they form after the degrees. So nano is the nucleus, it's the dissemination nucleus of nanotechnology that was formed by micro and nanotechnology students.
Thank you.
That's quite nice. Well, my history in physics and optics go for a very long time, and I'm Brazilian, so I came to INL almost 3.5 years ago, and when I was during my master's, OSA was starting a program that's called Student Chapters, and we were actually the second student chapter from Brazil. So I'm one of the 6 founding members of the Brazilian student chapter, and we have started an annual symposium, which is quite nice. They still do it. They just celebrated 10 years of the symposium a couple of years ago. I'm not going to say how old I am. And they also did they were doing, as everybody is doing, celebration for the Day of Light. They were doing a series of web seminars. Last year, I participated in one of those. This year, they're having it again. And SPIE, which is also another photonics-based society, also has a program. So, and now both SPIE and OSA are working, and the student chapters are actually working together. So it's quite nice when you have like a physics and optics based group and you can create your own student chapters. They give you a lot of support regarding having visitors and going to the annual conferences and learning new techniques and learning new things to communicate what you do in optics to the society. So it's very interesting for students, especially early years graduate students, because it helps you understanding how this interaction and the networking is important. Okay, so it's not just being in your little group. You need to meet people, you need to talk to people, you need to interact. That way you're gonna be able to know more and find more people. So it was through the student chapter that I was able to go to MIT for a 1-year internship doing my PhD, because I had a chance to talk to the supervisor. So it helps quite a lot.
Thank you very much for this feedback. So this is exciting. And so if you have any more questions for us concerning career path, how we ended up doing what we do, or if we, if you have any questions about, the job as a researcher, or the training as a research student, photonics or nanotechnology student, please just ask us here in the chat or Q&A. If you don't have more questions, I'm sure we are all available to answer your questions later. And I would think we would start with the quiz. So Ricardo is our quiz master today, so he will guide you through this. Please make sure you install the app or you are using a browser where you can now log in. The game PIN number is the 604010, but I think Ricardo is explaining this. So some of you are already registered. The panelists themselves, speakers, are excluded from participating as usual. So Ricardo, can you?
I think we should actually make this like a joint activity, and you help me cheer up. You all help me cheer up our participants. So right now we have nine participants. We had more at one point, but maybe because this screen was not yet being shared. So so now it's the time. You can either click on the link that I've been posting on the chat, or you can join us through the app if you want to keep looking at Zoom. You can the interactivity is probably as good on the desktop as it is on the app, but now it's the time to join, and we'll maybe wait just a little bit longer to see if more people can join. So if you don't see your name, go ahead and click. But if you do, then that's good. So some of the names have actually been here for a long time. Others have been popping in and out, maybe a little bit uncertain if they were already in the game. So let's see who's the winner.
So maybe we can explain just a little bit. So there will be questions from multiple choice to yes or no, or correct, not correct questions. And there will be a certain short limit of time for you to answer. So it is also important, so if you're really competitive and you would like to win the quiz, you should be answering as fast as possible. So you get more points the faster you click.
And you also have combo points for getting correct answers in a row. So essentially there will be a question, I will read it. And then very soon after you'll see the answers, and I will not read the answers. I will leave that to each of you to read and decide and click as fast as you can in the correct answer.
Remember, there can be prizes, so let's participate.
So we already have 15 participants.
Yeah, I would think we
are ready.
We wait 20 seconds and 20 seconds more. If
anybody is stuck trying to install the game, just write it quickly on the chat so we wait a little bit longer. Otherwise, 20 seconds and we'll start. I don't know, can you actually hear the song, the little theme? There's no music. Okay. One more participant.
Okay.
I don't know if some of these participants
I think we can start.
Okay, let's start.
20 seconds are over.
Okay, so let's go ahead and start. See how this goes. Everybody ready? Come on, question number 1. What is the official language at INL? Remember, there's a maximum time of 20 seconds, but you get more points if you're faster. One last person to answer, and time's up. So almost everybody got it right, just one wrong. I think we'll see a little bit of a, here. So we have already a podium up to 5. Now remember, correct questions in a row will give you more points. Fast questions will give you more points as well. Second question, still about INL. What is done mainly at INL? See, people are answering really, really fast. All 15 answers are there. I will not press skip because I'm afraid this will skip the question. In 2 seconds, here we go. 13 correct answers, 2 wrong answers. Let's see how this affected the scoreboard. There's been quite a shift in position. Pedro Veloso now in first place, MFC and nobody in third place. Moving on to the third question about the first talk, Alessandro. How many layers does the record 6-junction solar cell device contain? This is a delicate memory.
Yeah, it's also kind of a trick question on
Trick
purpose.
question. I knew the question and I heard the answer in the talk, and it's a trick question.
Yeah, indeed.
Everybody got it right. Actually, no. Actually, no. This is the right one. This has been so far the most difficult question. One can tell from the statistics. Let's see how this affected. Nobody is apparently on a streak. 3 correct answers in a row. You can see here how the combo correct answers will give you more points. Second question about Alessandro's talk. How long does it take to form a layer with the MBE background pressure of 10 to the minus 11 millibar? Some people still trying to decide.
Yeah, they're taking their time this time.
Yeah, this is a good scheme. So I invite the speaker who's talking, whose question is about to join the fun. Usually I stay quiet for a little bit because people are thinking. So also very difficult question. Apparently only 4 people got it right. Most of everybody got it wrong. And let's see, nobody still getting it right. I'm afraid nobody's going to win this. If you see the pun in there. So quite a point difference here. Let's go to question number 5. I believe this is about my talk. How long does it typically take to deposit a 1000 nanometer thick solar cell by MBE? Still about Alessandro's talk.
Me.
Way to make it more difficult to read 1000 nanometers. Just so it looks like it's still in the nano scale.
Yeah, exactly.
There we go. Man, your questions are hard to answer.
Good.
6 people got it right. At least the majority of everybody got it right. Nobody is no longer on a correct answer streak, but still quite far ahead.
Good.
It's a shame we cannot see the rest of the leaderboard, but yeah, you probably, I don't know if you can see it in your own device or not. But let's move to the next question. This one, I think it's then about my talk. OFDDD takes inspiration from a famous model. Which one is it? Some people still trying to decide. For answer 2 answers remaining. There we go. Let's see. 7 people got it right. Not bad. So let's see, what did we get here? The Maxwell oscillator model. That was the trick one. There is no Maxwell oscillator model. MFC is now on a highest answer streak of 3. Congratulations. We can finally see some shifts in the leader scoreboard. Let's go to the 7th question. What wavelength range can be simulated using OFDTD? See a tricky question again. Well, taking its time to choose. Let's see here. Oh my God, this is nearly a random answer. It's because I've said all of these. So yeah, indeed, it's any wavelength. There is no inherent limitation to the wavelength that can be simulated with a model. Let's see here. Alves is now on the 1st position, MFC in 2nd, and nobody in 3rd on a downhill climb from the top of the scoreboard. Let's go to the 8th question. Last about my thing. Which of the following leads to a false statement? OFDTD is. can see here how the false complicates the process choosing the answer. So the correct answer, limited to photonic applications. That is the only false statement. It is not limited to photonic applications. All the other ones are correct, and that's probably why there's been so many votes. Nobody's back on top, but still at a close margin, with Alves in second and MFC in third. And now to the 9th question about Joana. Joana's talk, the PIC evanescent field is a product of. PIC standing for Photonic Integrated Circuit. Let's see here. Most people got it right. Total internal reflection. Congratulations. And let's see now. Joana, you are welcome to join in the fun. Alves is back on the first place. Adri is also climbing the success ladder here. We're almost at the end, going to the 10th out of 13 questions. Pedro Veloso is the highest climber, even though we cannot see it here. Second question about Joana's talk. Integrated photonic structures are employed in photonic biosensors to.
I think I made them easy, but let's see.
I wouldn't consider this an easy one. Let's see. Get an analyte-dependent signal. That was the most popular answer, but actually the correct one was to interpret the signal.
Yeah, but I understand how they can get it confused because of the talk. So the waveguide, you still get an analyte-dependent signal. However, you won't be able to really understand what's going on.
And that was a trick question then. Apparently,
Yes.
Alves was the only one to score, at least in the
Nice,
in the scoreboard. But still, MF is the highest climber. So let's go now, last but not least, about the facilities, the NBI facilities, 11th out of 13 questions, true or false? Any researcher can access the INL facilities by requesting access and receiving the proper training. This is a no-brainer. True or false? True or false? 2 answers remaining for the next 2 seconds. I get the impression someone has already given up on the competition. 11 correct votes on the true. It is indeed true that any researcher can have access to the facilities simply by requesting access and receiving the proper training. Congratulations to those that got it right. You can see here Alves is on a fire up, still securing his first place in the leaderboard. And a second question about the facilities. Which technique is the NanoLive 3D cell explorer microscope based on? Let's see, I can think of a few people who will get this right. Almost everybody got it right. Holotomography.
Holotomography.
You can tell that this is not my field of expertise here. Fantastic. So almost everybody got it right. Let's see how the time is affected. Whoa, finally nobody is again in the first place. Probably the best contestant to get a prize here. I got a feeling I know who this nobody is. Alves in second and MSC still fighting for the leadership. And to the final question, what is the contrast parameter in 3D holotomographic imaging? This was also widely repeated during the talk, even though I read it really the wrong way. 1 second to go. And almost everybody got it right. Refractive index, indeed. One can do 3D refractive index mappings with all the cool representations that we've just seen, and probably a lot more. So let's see, how do the final results look like? MFC in 3rd place, Alves in 2nd place, and finally, the big International Day of Light winner, nobody. With runners-up on Leston and Adri close behind the 3rd place, in the 4th and 5th place. Congratulations. So yeah, how do we go from here?
Unfortunately, nobody won, so we keep the prize.
Nobody is getting a prize.
Or nobody reveals who he is, and if he or she likes to reveal the identity, he or she will be promoted into the panel here, and we can shortly discuss together. But if not, that is fine. Please contact us who you are. Now we get emails from everyone about the prize, so I think you have to reveal who you are. Otherwise, unfortunately, we cannot hand out a prize.
I think it's already up. It's Kartika.
Sorry?
I think it's already up. No?
Well, I think we are not able to hand out a prize this year. We're very sorry. That was nice to see you. Next time, please register with your name, and we can also we are happy then to provide a prize. It was a lot of fun to celebrate with you this year's Day of Light, and as you can see, it's time to enjoy the late sunshine now. Also here in my office, at least, the afternoon, evening sun is entering. We thank you for participating, and we are happy to welcome you back next year. It was a great pleasure to have you all participating, the speakers, Alessandro, thanks, Joana, Ricardo, Mariana. It was very insightful and fun to have these discussions. And for all those that missed the talk, I'm sure we will be able to share also a recording. So stay tuned, check in our YouTube channel, and if you have any questions, contact us. Thank you and goodbye. Bye-bye.
Goodbye.
Thank you. Bye-bye.
Bye.